Hello and welcome to Chemistry with Dr. Clark. In this video, I would like to talk about how to represent atoms using Lewis dot diagrams. Now, if you've watched some of my other videos, we do discuss how to represent atoms and ions using Bohr diagrams. So perhaps we should start there. Let's say that I would like to draw a Bohr diagram for, let's say, sodium. So if I look up on my periodic table, let me pull out my periodic table. Sodium is element 11, which means that it would have 11 protons and 11 electrons. So if I want to draw a Bohr diagram, now if you are not totally sure of Bohr diagrams, I do have a video called How to Draw Bohr Diagrams. You might want to pause this one, go back, watch the Bohr diagram video, and then come back. Okay, so if you're going to draw a Bohr diagram, you have 11 protons. Those 11 protons go in your nucleus here in the middle. And then the electrons live in rings or orbitals around the nucleus. So let's draw a couple. Now the rule is your first ring or first orbital can take 2 electrons. So my first 2 electrons will go here. You had 11. You've just used up 2, so now you're down to 9. The second ring can hold 8 electrons. You've got more than 8, so this second ring will have 8 electrons. 7 and 8. So you've used up 8 more, you're down now to 1. That last electron is going to live in the third ring, the third orbital, right here. Now I can use this Bohr diagram to represent an atom. It shows me my nucleus, it shows me my electrons, it shows me that the electrons are living in the first orbital, 2, second orbital, 8, third orbital, 1. It shows me my number of valence electrons, right? Valence electrons are the number of electrons in the outermost ring, and there is 1. Now, if you've had to draw these things, if you've watched me draw mine, there's a couple of things that stand out. First off, they take up a lot of space. Okay, they're not compact. The second thing, drawing these circular orbitals, yeah, that never works out very nice. Okay, these here are probably my best circles, and they don't look the best. So what we'd like is a way to represent this atom that's a little more compact and a little easier to draw. Now, that's where my Lewis dot diagram comes in. It's a much more compact, a much faster way to draw this atom. Now, we are going to have to talk about what are we going to include and what are we not going to include. If I'm talking about a chemical reaction, if I'm going to take my sodium and I'm going to react it with something else, when those two atoms come together, the first interaction is at the very outside of the atom. So it's going to be the very outside of my sodium reacting with the very outside of the neighboring atom. So when I look at this picture, I really don't need to know anything about the protons, because when they interact, the protons are right in the center. The protons are not involved in the chemical reaction. Really, I'm also not worried about these inner electrons, right? If I look at this inner first ring of electrons, that's in the middle of the atom. When my two atoms come together and touch, these are not the electrons that are involved. When I look at this second filled orbital right here, same thing. That's in the center of my atom. When my two atoms come together to interact, it's only the very outer piece that touches. It's only my valence electron. So when I'm drawing this picture, why am I spending time drawing protons and showing you the inner core electrons? Because they're not important. They don't participate in chemical reactions. The only electrons that I really need to show is the outermost electrons, the valence electrons. So when we do a Lewis dot diagram, really the only electrons that we're going to be interested in are the valence electrons. So you're not even going to draw the nucleus, you're not going to draw the first ring, you're not drawing the second ring. Any ring that's filled, you don't have to draw it. The only one that you're going to draw is this outermost ring. Now, the number of dots that you're going to put in your Lewis dot diagram will be the number of valence electrons. So if I was going to draw a Lewis dot diagram for sodium, I'd only have 1 dot because there's only 1 valence electron. If I was drawing something that had 2 valence electrons, I'd have to have 2 dots. Now, when we do a few examples of these, the electrons are going to be arranged according to Hund's rule. Hund's rule only becomes important if you're talking quantum mechanics. So if you do want to go on and look at the quantum mechanics videos, I do have a couple on quantum mechanics. It talks about Hund's rule, the Aufbau principle, and the Pauli exclusion principle. But we will mention this briefly as we go through. Now, the other thing is, this is known by many different names. My personal favorite is Lewis dot diagram, because the diagram's all about the dots, and Lewis was involved. So that's the name I like. But you can call them Lewis electron dot diagrams, which is a bit of a mouthful. You can call them just electron dot diagrams, or just Lewis diagrams, or you can call them Lewis structures, right? So they have a wide variety of names. Depending on what textbook or teacher or assignment you're working on, you could see any one of those. All right, so let's actually do a problem. So if we talk about sodium, which we just drew, let's redraw my diagram. Sodium is element 11, so it does have 11 protons. If you have 11 protons, you have 11 electrons. So 1, 2, 8 in the next ring, 5, 6, 7, 8. That's 10, right? 2 plus 8 is 10. I have 1 left over, so that's my 1 over here. So basically, I've redrawn just a much neater version of this. This was me freehanding. This is me a little bit more organized. So the way this works, you have to have something that represents the nucleus and the filled orbitals, that first and second orbital. And what we've decided is that we're going to use the symbol for the atom to represent the nucleus and the filled rings. So for this one here, the 11 protons, the first filled ring, and the second filled ring, all of that is represented by the Na. Because really, none of this participates in a chemical reaction. And because we don't want to be drawing rings, because I could draw a ring around this and just put the 1 valence electron, but that's a lot of work and it's messy. So I'm just going to show that there is 1 valence electron. So this is a Lewis dot diagram, and it's showing you exactly the same as this. This shows you that you have 1 valence electron in the outermost orbital. This also shows you that you have 1 valence electron in the outermost orbital. Okay, let's try aluminum. So aluminum is element number 13. So aluminum does have 13 protons, which means that aluminum also has 13 electrons, right? It's an atom. It has to be electrically neutral. 13 positives, 13 negatives. So if we keep kind of a running tally, 13, I'm going to put 2 in the first orbital, because the first orbital can hold 2. That leaves me with 11. The second orbital can hold 8, and well, I've got way more than 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so just used up 8 more. That leaves me with 3. This third orbital can hold 8, but I've only got 3. So 1, 2, 3. Right? I could put in up to 8, but I've only got 3 left over. So this is a Bohr diagram for aluminum. Now if I look at it, here's my nucleus. In a chemical reaction, not super important. Here's my first filled ring. Here's my second filled ring. Again, filled inner core electrons, not important in chemical reactions. The only ones that are important are these outermost valence electrons. So instead of going to the process of drawing this, let's do our Lewis dot diagram. Let's shorthand it. So all of this core stuff, the nucleus and the first 2 orbitals, we're going to represent with the symbol for the element Al. Now the best way that you should think of this, think of it like a table. Okay, so if you're sitting at a table, a perfectly square table, this table can seat 8 people. So there's 8 people that can sit at the table. You've got 2 seats here on this side, 2 seats on this side, 2 seats on this side, and 2 seats on this side, right? So it's kind of like you're looking down on a kitchen table. And that kitchen table has 8 chairs around it, 2 per side. Now, it's not an accident that there's 8. How many electrons can you put in the outermost ring? You can put in 8. How many spaces do you have around your table here? 8. Now, this is what you have to imagine, is that your aluminum is sitting right here. So when you put in your 3 electrons, you're allowed to put up to 2 per side, right? 2 on the bottom, 2 on the right, 2 on the top, 2 on the left. You cannot put 3 electrons on a side, right? If you do watch my videos on quantum mechanics, it does talk about how orbitals can only hold 2 electrons maximum. That's what this is related to. You don't need to know quantum in order to do this. All you have to remember is each side of the symbol can only hold 2 electrons. That's it. Now, this is where Hund's rule comes in. Hund's rule is basically sitting next to strangers on a bus. Okay, if you get on a bus and there's people sitting on the bus and you don't know anybody, you're most likely to sit in an empty seat rather than sitting with someone you don't know. Electrons are the same way. When you put electrons here around this table, if you put an electron here, okay, let's put my first electron here, then the second electron will not go here unless it's forced to. Okay, you do not pair up electrons unless you got no more empty sides, because the electrons don't know each other, right? If you got on a bus and there were some empty seats and there were some filled seats, you're going to sit in the empty seat because you don't know the person, right? You're not going to sit with someone else if they're the only person on the bus. So when I put in my second electron, I'll put it here on this side. When I put in my third valence electron, let's put it on the other side. You're never going to have 2 electrons on one side of the symbol unless you have no more empty spaces. So for aluminum, because there's only 3 electrons, you can put 1 on the right, 1 on the bottom, 1 on the left. Okay, if we, let's see. Oh, oxygen's coming up. It'll talk about this a bit more. But this would be the Lewis dot diagram for aluminum. Aluminum has 3 valence electrons. I show 3 valence electrons, and you will notice that none of them are paired up because you don't pair them unless you have to. That's Hund's rule. Okay, so let's flip over to the next one. If we talk about oxygen, oxygen is element number 8. You got 8 protons, which means you got 8 electrons. The first 2 electrons go in the first ring, so you had 8, you used up 2, you got 6 left. This second orbital can hold 8, but you've only got 6. So 1, 2, 3, 4, 5, 6. That is a beautiful Bohr diagram. Still, too much work for us. I'd like something simpler and smaller. So we're going to represent the nucleus and this first filled orbital just by the symbol. So O for oxygen. Now, I do have to put the valence electrons, the outermost electrons, around it. And like I said before, you're allowed to put 2 per side, and you don't pair them up unless you have to. So 1, 2, 3, 4. Out of the 6 valence electrons, I have enough room to put in the first 4 without pairing any of them up, right? Because there's 4 sides, so I put in my 4 electrons. Now, you do have 6. I got 2 more, which means I have to start pairing them up. This one will have to pair, and this one will have to pair. So now I have a total of 6. 1, 2, 3, 4, 5, 6. And I have kept them as far apart as I can, and I only paired them up when I had to. Right? Think about it as getting on the bus. If you get on the bus and every single seat has somebody in it, then even though they're all strangers, even though you don't want to sit with someone, you don't have a choice, right? After I put in that first 4 electrons, electron number 5 had to pair up because there was nowhere else for it to go. All right, let's do chlorine quickly. Chlorine has 17 protons, so it has 17 electrons. 2 in the first ring, that leaves me with 15. 8 in the second ring, 5, 6, 7, 8. That leaves me with 7. And this third ring can hold 8, but I've only got 7 electrons left. So 1, 2, 3, 4, 5, 6, 7. Right? You can hold 8, but you've only got 7. The 17 protons, the first filled ring and the second filled ring, not really important to us. So I'm going to represent all of that by the symbol for chlorine. The only thing I'm really interested in is the valence electrons, the outermost ones. The outermost valence electrons, there are 7. So I need to put 7 dots around the chlorine. 1, 2, 3, 4. The first 4 go on 4 different sides of the chlorine. It's only when I get to number 5 that I have to start pairing it up. So you pair, and you pair. Now you've got 7 electrons. 1, 2, 3, 4, 5, 6, 7. That's the Lewis dot diagram for chlorine. Now at this point you should be thinking, hey, Lewis dot diagrams, they're great. They're compact, they're easy to draw, I love them. Bohr diagrams take up a lot of space, my circles never look good, I'm not super happy with those. But I feel like at this point I'm kind of stuck. Like, if I don't draw the Bohr diagram and show where all the electrons live, how am I supposed to know how many valence electrons I have? Right? How can I skip this? Well, turns out that your periodic table is built for that. If you look at your periodic table, and I have mine here, on the top of each column, on the top of each period, sorry, not period, each group, periods go across, groups go up and down. So each column, each group, there's a number on top of it. So there's one set of numbers that go from 1 to 18. So 1, 2, 3, 4, 5, 6, 7, 8, 13, 14, 17, 18. Those numbers, not super useful. The ones with the A's and the B's, though, those are the ones you're going to love, right? This is 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. Well, let's go back here for a second to the problems that we've already done. Sodium, right here, was in group 1A. It was in group 1A, and it has 1 valence electron. If I look at the aluminum, aluminum is here. Aluminum is in group 3A. So 3A. Oops. 3A. They do use Roman numerals sometimes. So 3A. It's in group 3A. It had 3 valence electrons. If we look at oxygen, oxygen is in group 6A. VIA. If it's in group 6A, it had 6 valence electrons. If you look at chlorine, chlorine is in group number 7A. VIIA. It's in group 7A. It had 7 valence electrons. If you look at your columns, the A letters tell you how many valence electrons you have. If you're in group 8A, you have 8 valence electrons. If you're in group 4A, you have 4 valence electrons. If you're in group 2A, you have 2 valence electrons. It only works for the A's. It does not work for the B's. The B's here are your transition metals. They do their own thing. But for the A's, the number that goes with the A tells you your number of valence electrons. So that means that it makes my life a whole lot easier. Ooh, I have too many periodic tables. Like for this one here. If I look at the 2A group, the column that starts off with 2A, it has beryllium and magnesium and calcium and strontium and barium. If I were to draw the Lewis dot diagram for magnesium, magnesium is element 12. 12 protons. If you've got 12 protons, you've got 12 electrons. So 1, 2. Put 8 in your next ring. 3, 4, 5, 6, 7, 8. So that's 2 plus 8 more is 10. That means I've got 2 extra electrons right here. Right? 2 plus 8 plus 2 is 12. 12 electrons to go with my 12 protons. You've got 2 electrons in your outermost ring. So because you have 2 electrons in your outermost ring, your Lewis dot diagram should have 2 electrons. And you do not pair them up unless you have to. So I'm going to put one at the top and one on the right. Now, drawing out your entire Bohr diagram in order to decide how many valence electrons you got, that's a lot of work. But if you remember the trick that the group number tells you the number of valence electrons, then the rest of these become very quick. Calcium is in group 2A. It has 2 valence electrons, 1, 2. Strontium is in group 2A. It has 2 valence electrons, 1, 2. Barium is in group 2A. It has 2 valence electrons. Now, in addition to being more compact, easier to do, neater and tidier, the other advantage that this has, really Bohr diagrams only work for the first 18 elements. So on your periodic table, only up to element 18, argon. First 3 rows, Bohr diagrams work. Once you get past element 18, the Bohr diagrams don't really work anymore. Okay, so really if you wanted to do a Lewis dot diagram for barium, you can't draw the Bohr diagram first to figure out the number of valence electrons. For barium, the only way you're going to know the number of valence electrons is by knowing that the group number is related to the number of valence electrons. Okay? And I believe I have one more set. Let's talk about the noble gases. Group number 8A, the very last ones over on the side of your periodic table. If we were to draw the Bohr diagram for neon, neon has 10 protons and therefore 10 electrons. 2 in the first ring and 8 in the second ring. 2 plus 8 is 10. Now, this has 2 filled orbitals, like they're completely filled. This is one energetically stable element. This is a happy element. It's the reason why your noble gases don't tend to react with anything, because they have completely filled rings. That's what all atoms want. Now, if we talk valence electrons, the outermost ring is your valence. This outermost ring is completely filled. So this outermost ring has 8. So if I were to draw them here, my first 4 go on 4 different sides of the neon. I don't double them up until I have to. So that's 4, 5, 6, 7, 8. 8 valence electrons. Every single possible spot around that neon is filled because this is the maximum number of electrons that I can have in that ring. Okay, so if we work our way across, I don't want to be drawing Bohr diagrams. So if this is group 8A, then they all have 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. That's the Lewis dot diagram for argon. For krypton, it's in group 8A. It has 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. That's my Lewis dot diagram for krypton. Xenon, still in group 8. So it has 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. If you remember that your group number gives you the number of valence electrons, then your Lewis dot diagrams are easy to do. As always, thank you for joining me here at Chemistry with Dr. Clark.